Hello, this video is about beam deflection. And so think about it. If you have a cantilever beam and you have a concentrated load at the end, so imagine a diver is at this end of the diving board, and what happened to the beam? It's going to be deflected, right? It's going to be like this. So today our goal is to figure out how much deflection happens. For example, at this end, this is going to be the deflection. And the deflection here, we're using a symbol V. Don't confuse that with velocity or shear force. And here V is considered as deflection, I know. So also, for example, what's going to be the point 1 here? What's the deflection? That would be deflection here. So then in other words, at every single point of the beam, they're going to have a different deflection. Obviously, for this cantilever beam, when you have a point load at the end, you will have the maximum deflection at the end. So V here for deflection is going to be a function of X. X is going to be along the axis of the beam, because at every single location you're going to have a different deflection, right? So for any example, if I have a simply supported beam and we have a concentrated load, and this beam gonna be deflected like this, and of course you will have maximum deflection right in the middle. And so again, you will have deflection as a function of X. So that's our goal today, trying to find this function for different loading. And here we're going to use our calculus knowledge. I will start from the equation what we start with. And here, if you want to know how this equation coming from, it's basically using use some of the calculus knowledge. But here we go. It's m over EI is equal to a double derivative over with respect to x. Okay, so we can potentially write down this as m is equal to EI, and I'm going to write v double prime. So that's going to be the equation we'll start with. Our goal is trying to find the function for v, right? So we need to integrate this. We need to integrate twice. So in other words, we'll have, after integration, we'll have EI. V is going to be equal to double integral of this m. M is internal bending moment, and it's a function of x, as we learned from low shear bending diagram, either from analytical or graphical approach. You know, the bending diagram is different for every location. So it's function of x, then dx. Okay. So here again, I want to emphasize this V is deflection, is how much deflected for the beam. And one more, V prime, if it's like a single derivative, that means it's rotation of the beam. Or it's considered as a slope, right? Slope of the deflection, or slope of deflection, because it's derivative. And sometimes this V prime in different textbooks they may use as theta x, theta. So no matter what, we know that's going to be indicating the slope of the deflection or rotation of the beam. Okay. So knowing that, we're going to use an example to see if we can find deflection. So the example we will be using is going to be this cantilever beam with the concentrated load at the end, P. And this length is L. First step we need to solve is figure out the reaction support at this fixed support. And if we call this A, and we can quickly do a moment about A. And since this is fixed support, we're going to assume it's going to have a moment that direction, MA. So in this equation, we'll have, if we do moment about A, equilibrium, we have this MA due to the fixed support, excuse me, and then you have P times L, and it's clockwise, so it's in minus, equal to 0. Then you find out this MA is going to be equal to PL. Okay. Then we're going to write it down. This MA is equal to PL. Now what we're going to do is we're going to find M, internal bending moment. Because in order to find our V, you know you have to integrate this internal bending moment. So we need to find the internal bending moment as a function of X. And that's how we're going to use analytical approach to figure out using internal bending to figure it out. So we're going to make a cut anywhere. So when we make a cut, and we're going to draw our new FBD. So we have a choice to look at the left or right. So if I go with the left section, then where I cut, that's going to be X, right? It's random, arbitrary. And then I also have this moment due to the fixed support. That's what I have for external moment and external force and the moment. Now I needed to figure out the internal bending, internal loading. So I'm going to use red to indicate my internal loading. So thinking about the internal loading sign convention, we have to make a happy smile, right? M. And we have to make a happy smile. And what else do we have to do? We have to make it a tension, if we have a tension, to make a normal. And then for share, we have to make a clockwise rotation, right? That's going to be our internal loading sign convention. So now we're going to go ahead and solve them. Obviously, you can tell me what's N gonna be. Normal force is gonna be equal to 0 because that's only force at X direction. And then we're gonna look at force at Y, and we figure out share is 0. So the only thing we needed to solve is moment. If we do moment where we cut like we normally do, then we have this first one, MA, that's counterclockwise. Then we're going to plus this M right here. That's what we are solving, right? That's internal bending moment M. So I'm actually going to go ahead and put MX here because that's a function of X. So that's internal bending moment we are solving. That's counterclockwise, so that's MX. Then N and V, they go through that cut, so that will not show up in the equation. Then what do we have after all of that? Oh, I forgot one thing. I didn't finish. Sorry. We need to figure out we do figure out the internal bending, the moment at point A, but we didn't write down what's going to be the AY. Okay, so I need to go back to the first FBD, number 1, to finish what I need to do. We figure out the MA, but then forces at Y direction will have this AY going upward minus P that equal to 0. So we figure out AY, this vertical reaction is going to be equal to P. Okay, now we have that taken care of. AY is equal to P. There's no AX because there's no X direction. So knowing that, I'm going to go back to my FBD number 2. When I cut it, I need to have that reaction at A here as well. And that is going to be equal to P. Okay, that will complete our FBD number 2. Sorry about that. So now go back to look at this one. My V is actually not right? for theta y direction, what's the correct version will be I have this P at point A, and we also have minus V equal to 0. Then I'll get, from here, I'll get my V is equal to P. Okay, good. Now, however, what we're really curious is about internal bending moment. So I'm going to focus on this word moment about we cut. So we start with MA, this moment right here, counterclockwise. And then we also have this, we're solving MX counterclockwise. And now I need to go back to figure out this P. And regarding what we cut, so that's going to be px, that's moment of arm, and it's clockwise, so it's minus that equal to 0. And again, be aware we're solving this mx, this internal bending moment. Mx is going to be equal to p, right? Px minus ma. And you already solved the MA from the first step is PL. So PX minus PL. Then we have a function for internal bending moment is X minus L. Okay. We achieve our goal. We find expression, analytical expression for internal bending moment. All right. So now we're going to go back to our governing equation here, trying to integrate, like how we decided to do over here, right? When we integrate, so that's going to be our third step. We're going to do our first integrate. When we first integrate, what would we get? We will get from this equation right here, we will have E, I, V prime, double become single prime after we integrate. And then we'll have M dx. And M is a function of X dx. So we'll have that. Then go ahead, substitute Mx in there. It's P X minus L dx. Okay. And then we'll continue to integrate. We can take the P out. P is concentrated load. That's a constant. And when we integrate, I can write down again. So P. Integrate X, we'll get X squared over 2. Integrate L, we'll get minus LX. And don't forget, when you integrate, you're always going to add a constant. We're going to call constant 1. All right? So that's our EIV prime. And again, V here is our deflection, beam deflection, what we are solving. Now, in order to find this constant C1, we have to use boundary condition. So boundary condition. We're going to thinking about boundary condition number 1. Now let's thinking about every single problem. They're going to use different boundary condition. For this one, when x is equal to 0, which means it's at fixed support, what do you think the deflection will be? Deflection will be 0. However, also, what will be the rotation? What will be the rotation of this deflection? Thinking about this graph, when you have a diving board, you have a concentrator right here, and it's going to be deflect like this, right? So what's going to be the slope? If I'm going to draw it, what's going to be the slope at that deflection, which is V prime? That slope is going to be equal to 0. As you can see, it's a horizontal line here. So this V prime is going to be equal to 0. That's going to be our first boundary condition. So put this condition, put x equal to 0, V prime equal to 0. Let's see what we can find out for C1. So V prime, for the left-hand equation, EI V prime, that be equal to 0. And the right hand, put x equal to 0. So P 0 minus 0 times L 0 plus C1. And then you realize our C1 here, constant, is equal to 0. Okay, so now the complete first integral give us EIV prime is equal to P x squared over 2 minus LX plus 0. So that's our first integration results. So we're getting close to figure out the expression for V, which is our beam deflection. Then you already know we're going to do the second integrate. When we do second integrate from this equation, what will we get? We'll get EIV. EI is a constant, right? E is elastic modulus, I is moment of inertia. And we'll have EIV equals entire thing here, taking P is a concentrated load, so can take it out of the integral, and we'll have all of that dx. Okay, so now we're going to integrate the right-hand equation. So x squared integrate become x cubed over 3, and then there's 2, so that'd be 6. Then we'll have Lx squared over 2. All of this, then we're going to add a constant. This constant we're going to call C2. And left hand is EIV. We just copy it down. In order to solve C2, we're going to come up with a second boundary condition. And the second boundary condition will be when x equal to 0. Earlier, we're using V prime because we are solving V prime. V prime is the slope of the deflection. And for x equal to 0, what will be the deflection at this fixed end? At this point, the deflection is there's no deflection, right? Because it's equal to 0. Because at the end, you have the maximum deflection. So here, we can easily come up with our second boundary condition. X equal to 0, this deflection equal to 0. Not only the slope is equal to 0, the deflection itself is equal to 0 as well. So knowing that, we plug it in. EIV, V is equal to 0, left hand is equal to 0. Right hand, x equal to 0. So x cubed over 6 is 0. And Lx squared divided by 2, that's 0, plus C2. Well, what do we get? Our boundary C2, our constant C2 is equal to 0. So don't let this fact to fool you. Not every single time the constant will be equal to 0. Every situation is different. You have to use the right boundary condition to find the constant. It just happened to be this time, both of them are 0. Sometimes, again, it's not. Okay? So knowing that, we can go ahead and write down our EIV, go back to this equation right here, is equal to P x cubed over 6 minus Lx squared over 2 plus 0. Then we are at the final step, right? We're going to find the deflection. So our V, that's going to be our deflection. Our deflection is going to be equal to P, all of this, divided by EI. So that's going to be our final answer for deflection. Okay, and that wrap up for our beam deflection problem. But actually, if you want to make this a little bit better looking, if we want to change this to be in a different way, I'm actually going to encourage you to get your book out and look at the beam deflection appendix. So in the next video, I'm going to continue from there to show you how to read the beam deflection table. It's going to be quite helpful. So as right now, we're done for this one. I'll see you in the next one. Bye.